Hi, good morning, good afternoon, or good evening, everyone, depending on where you are in the world. Thanks for joining us here today for the webinar. We are going to get started. By the way, this is Ryan Crodel at Valencell, your usual host. We will get started here in a few minutes. It looks like we've still got quite a few people logging in at the moment, so we'll give them a couple of more minutes and then get going. Thanks for your patience. We'll get started here in a few minutes. All right, this is Ryan Crodel again with Valencell. We've still got a few others joining, but in the interest of time, we've got a lot of great stuff to cover here. So we'll go ahead and get started. A few housekeeping items before I introduce Scott. As usual, please do submit any questions you have through the GoToWebinar interface. We have time set aside at the end to address all of those questions, and we'll cover all of those that come in. Please do. We like to keep this as interactive as possible. So please submit any questions you have or any topics you'd like us to dive deeper on as we go along here, and we will address those at the end. One of the most common questions we get is, will the slides be made available? And the answer to that is yes. We, as a follow-up to the webinar, we will post the slides on SlideShare and also post a recording of the webinar onto YouTube, and we'll send out links to both of those shortly after the webinar today, tomorrow at the latest. And so please do share that with anyone that may not have been able to attend that you think would be interested in the topic. So without further ado, let's go ahead and jump in. I would like to introduce Scott Hansen, who is CTO and co-founder of Ambiq Micro. We are really excited to have Scott here. He is not only a great speaker and obviously a great entrepreneur, but has some really interesting insights to share around the topic of low power consumption as it relates to wearable devices in particular. And not surprisingly, this is something we hear nearly on a daily basis, is how can we lower the overall power consumption and therefore increase the battery life of wearable devices that Valencell's technology gets built into. And that's a big reason why Valencell has chosen to integrate Ambiq's technology into our next generation biometric sensor systems. And so we're excited to work with Ambiq and excited to have Scott here. So without further ado, Scott, I will hand over to you, and we'll go from there.
Excellent, thank you. Thanks, Ryan. I'm happy to be here. I think that the title of the talk is pretty clear, but what I really want to do is I want to talk about the power problem in wearables first. I want to then talk about some of the companies like Ambiq have been solving this problem over the last several years, and then really what new use cases can be enabled as a result of this. So before I do that, I'd like to just briefly set the stage by talking about Ambiq Micro. So Ambiq is a company that's focused on building the world's most energy efficient chips, and wearables is a very important target market for us. And today we're playing across a wide variety of wearables. We build microcontrollers and Bluetooth SoCs for things like fitness bands. Huawei, for example, is using us across a broad range of devices. Fossil Group is using us in a wide variety of wristwatch devices. We're in sports watches as well, and then smart clothing is also an interesting application that we've seen pop up in the wearable space. So Spire, for example, is one of our customers shown in the top center there. But it's not just wearables that we provide chips for; it's the broader IoT as well. So smart credit cards that have batteries inside of them is one of the key markets for us. We've got animal trackers, which is actually remarkably like a fitness tracker for a person, but animal trackers that need to last for years at a time. We have customers building smart train car sensors that need to last for years at a time. We have customers building smart radiator sensors, smart meters, smart industrial sensors, again with multi-year battery life requirements. So the common thread through all of these is that you've got to do a fair bit of work in a tiny package across months, years of battery life. So very steep challenges, and definitely wearables are among the most challenging out there because these are devices that can't just sense once every minute and sense at relatively low data rates at that, but these are devices that are increasingly running all the time and capturing a lot of data. Valencell is a great example of a company that's capturing tons of data every second, and we've got to have something to do with that. So we'll talk a bit more about that later. But the broader Internet of Things is this trend that's been certainly emerging over the last several years, and we've probably all seen plots like this that show the fantastic number of billions of devices that are going to be emerging soon and are already here. And whether you believe these numbers or you believe some discounted version of these numbers, the bottom line is always true, and that is that there are going to be billions of batteries out there that need constant replacement. So we already see smart door locks and our wearables and our smart credit cards and all sorts of devices that are going battery powered. And if we have to keep multiplying that every year and increasing the number of batteries that are out there every year, we're going to have major problems if every day, month, year we're out there replacing batteries. As an example, we're talking to a lot of companies right now that are trying to enable the smart city, and they want to put hundreds of thousands or even millions of devices out in a city. And if you're a municipality that has to manage all of those devices and send a truck, roll a truck every time that one of those batteries goes down, you're going to be very concerned about power consumption and the costs associated with poor power consumption. Now, on the flip side, if we're talking about wearables, this is exactly the kind of thing that causes wearables to end up in a drawer. If battery life is insufficient, if I can't make it through a week or my month or whatever my key target is, that wearable device is going to end up in a drawer, and that's a problem that's got to be solved. And the strain on wearables is, or the battery strain on wearables is something that's been growing over a number of years. So if we all remember fondly back to the old Timex Ironman devices, which still sell today and still have updated versions of today, we're talking about relatively simple devices. So segment displays, segment LCD displays, maybe in a high-end device, we're talking about a simple matrix LCD display. But we're also talking about very basic watch functions. So stopwatch, alarms, and maybe a basic calendar. But the upside of that is you get multi-year battery life, and actually the wristwatch industry was the place where low power design really took off first, where they were really pioneers in driving power down on all the components and the chips that are involved in it, the displays that are inside of it, and the net result, as I said, was 3 year plus of battery life, and you maybe didn't even worry about replacing the battery. Maybe you just threw the watch out and bought a new one at the end of that. Now, if we fast forward to today and we look at the latest generation in sports watches from companies like Garmin and Suunto, you've got these really incredible wrist-based computers. Okay, they have the same basic watch functions, but they've added in a high-resolution display, which is in many cases color. They've added in constant motion and activity tracking, which results in which require accelerometers and gyros to be running all the time. You've got heart rate monitors from companies like Valencell that are putting strain on power budget. You've got GPS tracking, and this is really one of the worst. You can have 70 milliwatts of power going into a GPS tracker if you're not careful, or a GPS receiver if you're not careful. You've got altimeters, thermometers, and then also the latest integration is Bluetooth radio so that we can maintain a constant connection to our phones and get notifications. So at the end of this, we've got days and weeks. In the case of the Garmins and the Suuntos in the world that have done a really good job of optimizing battery life, you've got maybe a couple weeks of battery life, 10 to 15 days or something like that. And this is a problem, though, that's only going to get worse. Okay, there's constant pressure on these companies to go smaller and thinner in their industrial designs, and that means batteries, which are really one of the largest things, if not the largest component inside of these watches, have to get a lot smaller. And that means a lot less capacity available for the chips inside of these devices. Probably the most interesting thing is new functions are constantly being added. And this is something we've seen in the phone space. Every year, Apple and Samsung and all their competitors roll out some new feature. And that basically has pegged battery life at a year. No matter how good technology gets, how good battery technology, IC technology gets, we're pegged at a day of life. In wearables, we may see much of the same. We're going to see functions constantly being added. It means things like adding cellular radios, adding new biosensors, more sensor analysis constantly done in the background. This additionally places strain on the battery. And then we're also seeing new use cases. Not everything in wearables is, of course, a wrist-based watch type product. There's also smart clothing, as I alluded to earlier when talking about Spire. And the use cases there are different, right? I might have 10 pieces of clothing that I want to tag, and I don't want to be constantly charging 10 pieces of clothing every week. So I've got to, in this case, maybe have a year plus of battery life. So again, that places great strain on batteries. And so the question is, how do we solve this? We're in the case of the phone example I gave, we're used to every year having something better and more functional than the year before, and that's driven by, in large part, Moore's Law and some of the innovations coming out of the chip companies. So what is our equivalent helper function here in wearables? The first thing you might look to is batteries. That feels the easiest. And it's a thing that if I can identify one component in the system and improve it, I get help. But the truth is that there is no Moore's Law for batteries. This plot here basically shows improvement in a variety of metrics over a number of years. And what you see is that the improvement in battery energy density is basically lagging way behind all of the other things like disk capacity and CPU speed and available RAM, which are all driven by Moore's Law. So we've got a battery that's improving at maybe a few percent per year. That's just not fast enough, right? I mean, I need something that's going to give me maybe a doubling of year in battery capacity, and that's just not happening out of the battery side. So we really have to go look at the other side of that energy equation. And what I mean by that is we have to look at the energy consumers, not just the thing that's delivering energy to the system, but we've got to look at the energy consumers. And if you break down a typical one of these systems, one of these wearable systems, you're going to find same types of chips. You're going to find some kind of power management chip that's managing the energy being drawn from the battery. You've got a processor of some kind. Maybe it's an MCU in the case of a lower-end sport watch or wristwatch. Maybe it's an application processor in the case of an Android watch or the Apple Watch. You've got a radio that is drawing some amount of power. You've got a display. There's all kinds of different displays, from your segment LCD displays to your electrophoretic displays to your really high resolution OLED displays. And then you've got all kinds of sensors, and this is probably the area where you've got the biggest variety. You've got heart rate monitor. I would even throw GPS receiver into the class of sensors because it's really a location sensor. You've got accelerometer and gyro and all sorts of other sensors that are emerging, it seems, annually. And if you look at all these components, all of them are actually really big power consumers. They're all consuming power that gets into the milliwatts. Whether you're looking at the display, it can be 10 to 100 milliwatts. You've got a radio today that's anywhere from 10 milliwatts to 30 milliwatts when transmitting and receiving. GPS receiver is one of the worst ones and can be, as I said earlier, 70 milliwatts or higher if you're not careful. And then you've got this power management burden that really lays over everything. You've got 10 to 20% of system energy just sunk in heat. You know, anytime I have to take a high battery voltage, which is usually up around 3.7 volts, and I've got to drop it down to something lower that a chip can use, whether that's 1.8 volts or 1.2 volts or whatever, I'm losing energy to heat. And that's going to be basically a 10 to 20% system-wide power tax that you have to pay all the time. So we need to compare this, though, against the typical wearable power budget and see if we've got a problem. And the truth is, no surprise to this group here, we've got a big problem. And first example I'll give is, imagine the 1 week wearable. It's some kind of smartwatch or sport watch that I want to last for 1 week. Let's assume that I've got a 370 milliwatt hour battery in here, and I'm running that 24 hours a day, 7 days a week. I get to a need for an average of 2.2 milliwatt power draw in order to make that. Clearly, this is a simplified view. I haven't accounted for self-discharge of the battery. I haven't accounted for peak currents in the system, degrading capacity. But for our simplistic use case here, we're talking about 2.2 milliwatt average power for that 1 week life. So very low, a lot lower than all of these components here. So quickly that says we've got to do some duty cycling. We've got to do some intelligent powering on and powering off. We've also got to work like hell to drive the power down on these devices. Where things become even more challenging, though, is when I look at the use case where I want to last a year. So that's the smart clothing use case, or the wristwatch use case. For example, the fossil group wearables. They've got to last for 6 months, a year plus, and you're looking at a battery that's maybe 675 milliwatt hours. They have to last for the 24 hours a day, 365 days. We're looking at 77 microwatts. So very, very low power. This is dramatically lower than what we were talking about before, and really places incredible constraints. So any way you look at it, you've got a major power problem that's got to be solved. But the good news is there's been a lot of progress over the last several years, and one of the most notable things that has helped drive IC power down, or drive the chip power down, has been Moore's law. So just like in the cell phone space, that was the engine that made cell phones possible and made PCs possible. It's also been an incredible driver for wearables and the broader embedded community. And for those of you not familiar with Moore's law involves every 18 months, which has now become 24 months, is now skewing closer to every 36 months, transistor size gets smaller. And that means that we can fit more transistors on a chip. It means that the cost per transistor goes down. It means that performance goes up, so I can run a lot faster. But one of the things that tends to be ignored is that power goes down as well. I'm using a smaller transistor, so the capacitances associated with it are smaller. I'm using smaller wires, so the capacitances associated with that are smaller. And then on top of that, because this transistor is innately faster, I can drop the voltage. And as I'll talk about in a little bit, voltage is really one of the primary energy knobs in a system. Energy is related to the square of voltage, so it's quadratic with voltage. So as I drop voltage, I get huge energy gains. And what you see is, if you look at this plot here, the black curve shows total energy as a function of technology node. So we're looking at the late 1990s quarter micron or 250 nanometer technology on the far left, going down to 22 nanometer technology, which was a few years ago, state of the art. And you see about a 50x improvement in energy over that time. Okay, so this is phenomenal. 50x. If you're a circuit designer and you do nothing but go from technology node to technology node and rely on TSMC or one of the other foundries to do your innovation, you can get a 50x improvement in energy. Now, the bad news is that's basically saturating. We're not going to get too much more of a gain in the near future. But there's been phenomenal gains, and I'll show in a couple slides just how much of a gain has been achieved in a typical system, but it's pretty incredible. Now, at the same time, these foundries, the chip manufacturing factories, haven't just made transistors smaller, they've also made them lower power or given us new flavors of low power transistors. So I'm showing on the left there a screen capture from the website of one of the big third-party chip manufacturers. And the point is, what you see is a lot of different threshold voltages, so a lot of different transistor flavors. Some can be used for high performance, some can be used for low power. But the point is that as a designer, I get a lot more choice. I can opt for high performance transistors for circuits that care about performance. Where I need low leakage, maybe something that's sitting on all the time, I can opt for a low leakage transistor. And so the number of varieties that we have available is really exploding, and that's been phenomenal for me as a low power designer. At the same time, these foundries are also innovating in the types of underlying transistors that are available. So one of the most fantastic innovations that's happened over the last 20 years has been the introduction of the FinFET. So you can see that it gets its name. The transistor is shown on the right there. The green thing is the source and drain with a channel in between. You can see there's an arrow pointing to the thing that's called a fin. So it's this vertical structure that comes out of silicon or out of the substrate, and you've got a gate that wraps around it. We won't go into the device physics behind this, but basically it's a near ideal transistor. It's much better transistor than the one we've been building for the many years before this, and it's innately a much lower power transistor. It can run at lower voltages. Remember that voltage is an important knob in driving energy down. The leakage current is incredible on it. So for those of you, many of you will know that as you go from old technology node to new technology node, one of the biggest problems that's happened is that leakage current has popped up. So standby current in your system has grown tremendously. So just leaving the circuit on but idle has been a major problem in the last couple of years. The FinFET actually, to a large extent, fixes that problem. It's a much lower leakage transistor and thus can be left in an idle phase more easily. So a lot of innovation coming out of the IC manufacturing side of things, and these are the kinds of things that we as chip companies take advantage of. And most of you probably are using FinFET transistors today. You've got a phone. If you've got a cell phone in your pocket from Samsung or Apple or one of the other leading companies, you're almost certainly you are definitely using FinFETs. Wearables are generally not there yet, but will be in the next year or two. You'll see FinFET devices pop up there. So expect a lot of improvements coming from this. So one of the other incredible areas where we've seen innovation on the circuit side is in dropping voltage. And I in particular talking about subthreshold design. This is something that was originated as a concept more than 30 years ago by the wristwatch community, but it was never really put into place in a comprehensive way. Ambiq is the first company to roll out subthreshold in a comprehensive way. And the concept is like this. In conventional circuit design, we signal with a 0 with 0 volts, and we signal a 1 with a much higher voltage, maybe 1.2 volts or 1 volt. And the result is I get a very robust system that can easily differentiate between a weak 0 and a very strong 1. And that one, the voltage on that 1 is much higher than the turn-on voltage of the transistor. Okay, in subthreshold design, we run at a much lower voltage. So instead of a 1 that is 1.2 volts, we're using a 1 that's maybe 0.3 volts or 0.5 volts or something in that range. We're never really actually turning the transistor on. So it's called subthreshold because we never quite exceed the turn-on voltage of the transistor. And if you look at textbooks, textbooks basically say this is not possible, or they teach the transistor as a binary on-off thing. And the truth is that the transistor works down in this subthreshold region reasonably robustly, but you have a lot of challenges that pop up. Exponential sensitivities to temperature and voltage fluctuations and manufacturing variations. And it's a very hard regime to design in. So we've worked very hard to solve that problem. But the result is we get a quadratic energy reduction with voltage. So we, in this case, get more than a 10x reduction for this example. It can be used both for digital circuits and analog circuits. So I can build a CPU using near threshold or subthreshold circuits. I can build analog interfaces using this. I can build oscillators, regulators, all sorts of things. And so I can build a very wide swath of ICs with dramatically lower energy. So when you bring all of these solutions to this power problem, we get fantastic improvements. And I want to give an example. So TI launched the MSP430 a long time ago. I take the example of one that was launched in 2003. These guys were innovators, okay? I mean, they were the first low-power core. This was the one that everybody measured themselves by, and they've been very successful as a result. And if you look at that core, it was 16-bit proprietary core, ran at 8 megahertz, 60 kilobytes of flash, 2 kilobytes of RAM. And you can see the power numbers, 440 microwatts per megahertz. And then if we normalize that to the amount of work it's doing, so use CoreMark as a benchmark and say how much work it's actually doing, we're looking at 400 microwatts per CoreMark. Because remember that every clock cycle of a microprocessor is not necessarily the same amount of work, right? A Cortex M4 does a lot more work in a single cycle than a Cortex M0. And so we have to account for that. Now, Ambiq launched in 2016 the Apollo 2 microcontroller. This went into production last year with some customers, and the processor core here was a 32-bit ARM Cortex M4, runs at 48 megahertz, so a lot faster, a lot more memory. Okay, so we're looking at a dramatic increase in memory. I'm sure that we look back at that MSP430 memory size and think, boy, that's a pitifully small amount. But all microcontrollers have increased memory size and speeds in this time. But the really interesting thing is you look at energy. So power consumption per clock cycle, which is, okay, that's not quite right. So power consumption per megahertz is 33 microwatts per megahertz. So that's equal to 33 picojoules per cycle. That's 13x better than what the MSP430 was doing. Now, the M4 does dramatically more work in a cycle than the MSP430. So you can see that if we look at, let's think about it in energy per unit of work, we're looking at a 29x improvement. Okay, so huge improvement. So over the course of 13 years, we see a 29x improvement in total energy consumption. I mean, that's fantastic. That's something that we can really put to work. And in part, this has driven the revolution that we've seen in wearables over the last couple of years, and will continue to drive revolution of wearables in the coming years. So one of the other energy problems that we've ignored so far is the radio problem. So we talked about IC energy. Clearly, a radio is an IC, and it benefits from all the innovations that I mentioned on the previous few slides. But we've also seen a set of other innovations introduced, probably the most notable of which is the introduction of new low-power protocols. So Bluetooth Low Energy is a great example, and one that's prolific and is quite prolific in wearables. The ANT standard that was introduced by the Dynastream guys and now owned by Garmin is been a great driver of innovation and extremely low power. And then outside of wearables, we see standards like Zigbee have popped up. So all of these are relatively similar in average power consumption. Today, when you couple that with duty cycling and some of the application level approaches and the IC technology improvements that I mentioned in the last couple slides, you can get down to the point where we're looking at average power on the order of 10 microwatts. Okay, this is incredible. So average power of 10 microwatts to maintain a connection with a phone. I've got a Bluetooth Low Energy connection that is every 1 second pinging my device to either send an idle empty packet or send some notification or some other update. I can do that for 10 microwatts today. This is really fantastic and gets us to the point where radio power in many wearables is just not even a factor. Clearly, there are radios use cases where we're streaming audio constantly, or we're trying to activate a cellular radio or something. But for the typical baseline Bluetooth Low Energy use case, radio power has ceased to be a problem, which is really incredible. And so we get now to another example of a major power consumer, which is display energy. And we've been stuck with segment LCDs and dot matrix LCDs, low resolution LCDs, for a long time. And the display quality has been not so great. Well, there's been some really interesting innovations on the display side. So electrophoretic displays have been one really cool innovation. This is most notably used in the Amazon Kindle device. And this is a bistable display that when power is removed still maintains its image. And I'm showing a image from E-Ink, which has been one of the most popular display providers in this space. So very, very low power. If you're updating once a minute or once a second, in the case of a wearable, the power can be extremely low. Now, there's a downside. The frame rates that can be achieved here are relatively low. So if you want to do some kind of animation or show video, it's going to be a problem. And the color depth on these devices has been relatively low, though innovation continues. So I don't want to speak for these display companies. They certainly are doing some excellent ongoing innovation. There's also some really new innovative displays emerging. So micro LED displays are devices that are emerging right now. Apple is rumored to be working on micro LED displays, and there's a variety of other companies that are working on these. So I do think that we'll see smartwatches introduce these types of displays in the relatively near future. And these are devices that use tiny LEDs, so micron scale LEDs that are placed in a matrix, and we basically only turn on what we need. We only transmit what we need. These are extremely low power displays, certainly not as low power as say like an electrophoretic display or the segment LCDs, but will be dramatic improvements over the OLED and LCD displays of today. And on top of this, we've also seen companies introduce motion detection and gesture recognition to activate displays intelligently. So maybe I've got a power hungry display, but if I only activate it when I twist the wrist and look at it, that's great. I think we'll see displays that are a little bit more intelligent and are maybe doing face detection or iris detection. And that will allow us to be even more intelligent and avoid burden on the user. But we do see a lot of continued innovation here, and I'm excited to see what will emerge in the next few years to continue to solve the display energy problem. So when we roll all of this up, it allows us to roll out some new use cases in wearables. And one of the first ones is the battery-free wearable. So we can actually use energy harvesting to power a wearable once my power gets low enough. And I'm showing a plot on the left from a Marlow commercially available thermoelectric generator. The scale is we're talking about milliwatts of power, and if you get down to temperature differential that could be reasonably generated in a body, we're talking about a few degrees and in the microwatts on power. So very, very low power is generated, but if our circuits can get down to the microwatt range on an average duty cycle level, then this is quite reasonable. And in fact, one of our customers, Matrix Industries, has rolled out the Matrix Power Watch that is powered by body heat. So very cool watch that uses thermoelectric integrated into the device. Still has a battery, okay? So you still have to have a battery there in the event that you take the watch off or body heat body heat differential is smaller than anticipated. But one thing I want to point out is that energy harvesting is very much a complex system challenge. So in the case of Matrix, they've got a heat sink built into the case. If you look at the case, you can see the heat sink is built right in there. So this was something where they had to design the entire system to be energy harvesting friendly. So the circuits that they chose to run inside, the heat sink that they developed on the outside, all a very interwoven complex system challenge. So whether you're integrating solar or RF energy harvesting or using a temperature differential, it's a complex system problem. But there are companies that are out there that are enabling this. We certainly work with a lot of them. Matrix is one of them, and there are others that are doing really interesting things here as well. Another interesting use case that pops up when I've got low power circuits available is the embedded coach. So we throw out a fantastic amount of data. I mean, it's an incredible. We discard so much of the data that these wearables collect that it's a real pity. So you think about an accelerometer or gyro collects maybe 70 kilobytes of data per minute, and we're throwing it mostly away. We're basically reducing that to a step count, maybe some basic context, but we're throwing it all away. If we could either store that data for analysis later or we could analyze it on the fly, then we could do a lot of really interesting things that would be useful for an embedded coach. Specifically, we could do activity recognition, but not just simple running, walking. We can do real detection of are you doing a push-up? Are you doing a pull-up? Are you typing? Are you in a meeting? There's all sorts of things that we could do. There's posture analysis. There's skills assessment. How good are you at shooting that basketball or dribbling the basketball or whatever? There's a lot of really interesting things that we could do if we could analyze that data on the fly. And I want to break here and say the Valence Cell are the world's best experts on heart rate data, and I know that they've got a lot of ideas on what could be done there. So Ryan, I'll just hand it to you for a second.
Yeah, and this is a really important point here about the enabling of new use cases when when power drops, and the capabilities, as Scott has talked about, the capabilities of these devices showing no signs of slowing down in terms of the number and type and function of the sensor systems that are going into these devices. And that's where you're going to start to see a lot of the innovation in the space is sensor fusion around putting data together from the heart rate monitor, the accelerometer, the gyro, the GPS, all of those things, and doing real-time analysis on the fly for those capabilities. We know very well, just from a biometric sensor standpoint, there's a tremendous amount of data that we collect and can provide to the host processor of the device that provide contextual or metadata around the PPG waveform, or the biometric sensor data specifically, that can add real value to not just an embedded coach use case, but also understand in more depth and with more granularity how exactly that person's body is responding to whatever activity they happen to be doing at that time, which of course can be recognized and identified through the accelerometer and the gyro. But then at a biometric level, understanding if a person's walking and their heart rate and their VO2 is changing, or their heart rate recovery or heart rate response is not responding or not performing like it has in the past. There's some deviation there. You can do things like alerting and identifying those issues as they come up. So and then of course you also add in the microphone piece of it, which Scott will get into in just a moment. And there's some obvious and very interesting interactivity capabilities between the user and the device itself that allow direct interaction with that data, or direct response to that data and that analysis that's going on.
Thanks, Ryan. Yeah, and as Ryan mentioned, you got the microphone data as well. So if we can analyze this data on the fly, and it produces a huge amount of data, so vastly more data than the other sensors up there, so 1.9 megabytes per second. If we can do that, though, we can do things like keyword detection and voice commands. Think of that as the entry point to your virtual assistant, to your virtual coach, but can also do complex context detection that maybe wasn't enabled by the motion or heart rate monitor sensors alone. And we could do things like respiration analysis. I can hear the breathing, and maybe I can use that to supplement the heart rate PPG data that we've already collected. But the key point here is that I can't store all this data on chip. I'm producing data at a rate that doesn't allow me to just store it on chip. And on top of that, if I want to do real-time coaching, I've got to analyze it on the fly and give real-time feedback to the user. So I'm at the point where I need to run a lot of compute cycles to consume all this data and deliver useful feedback to the customer. That's all possible today because of the tremendous, call it the 30x increase in energy efficiency that we've seen out of these microprocessors. So suddenly it's possible to do this complex analytics on the fly. Another interesting use case that builds on that is the intelligent wearable. And what I mean by that is introducing neural networks into wearables. They've emerged as this awesome tool, and there was a great talk by one of the guys from Google that's working on this, and he effectively said, if you're not trying to use neural networks to solve your problem, you probably should be. So it's a great tool, not for everything, but it certainly solves a wide variety of problems. Specifically for classification, that's one of the big use cases, but there are other ones. And I'm showing a screen capture from, for example, one paper that was using deep CNN neural networks for gait analysis. And you can imagine a variety of other use cases. So there's skills assessment, there's emotion recognition, there's activity recognition. There's a wide variety of use cases here. And we actually do have customers. I won't say which ones or how they're using them, but we do have customers today that are using neural networks, and they're forced though to use relatively lightweight neural networks. So I'll talk about this in the next slide, but neural networks can very quickly result in model sizes that are enormous, and that can be a pretty big compute burden. The Cortex M4 devices that we have today, or that are prevalent today in wearables, are really not tuned for neural networks, and as you'll see in a second, there's a need for something more. So I view this neural network opportunity as very much that, an opportunity, but it's also the next great energy problem to solve. We usually represent neural networks using the flow charts that I show on the left there, and the basics, for those of you not familiar, the basics of neural network are actually remarkably simple. You're doing essentially a set of multiplies and adds. So I'm taking a set of weights, so the W parameters in the figure on the left, and I'm multiplying them by a set of inputs and later a set of activations, and then adding the results together. So a bunch of multiplies, a bunch of adds, and it just turns into a giant data flow nightmare where I've got thousands or millions of parameters that I'm constantly moving in and out of memory and multiplying together, and then storing some results. So basic computation is very simple, but the number of MACs can be enormous. So just to quantify that, I'm showing neural network model information for several different applications. Keyword example, so this is a very common one that is in fact being used on microcontrollers like ours today. Keyword detection, so I'm detecting OK Google or one of the other keywords, and then I'm basically graduating to a much larger neural network that is doing more advanced speech recognition. In this case, though, to run a typical keyword detector might be 33 million MACs per second, or 33 million multiply accumulate operations per second, and that would be, technically a MAC is 2 operations, so it's really 66 million operations per second, with a model size that's on the order of 140 kilobytes. So what I mean by that is, to store the weights that represent the neural network requires about 140 kilobytes. Now, these numbers can be bigger or smaller depending on what you do. So we use today models that are smaller than this. We have partners that supply models that are much larger than this, that can be an order of magnitude or more larger than this. But this is a good representative one. And this is something that is today feasible on today's microcontrollers. And it's something, as I said, that we're doing today on our Apollo series microcontrollers. But when you start looking at some of the other options, let's take gate analysis. The model size is enormous on this one. Okay, so it's enormous. You run it at a relatively low frame rate, but the number of MACs per second that you have to run is actually quite high. So still probably on the edge of feasibility for some microcontrollers today. I think by the time you look at the overhead for data movement and data packing and unpacking, you're going to find that it's not possible in most embedded micros, but it's right on the edge of possibility. What is clearly not in the realm of possibility is the abnormal heart sound detection. So this one requires 4.6 gigamax per second. So that's 4.6 billion max per second. It's got a 12 megabyte model size. So this thing is a very large network, totally infeasible to run it on an embedded microcontroller. In fact, most application processors are incapable of running this model. And so you end up looking at something like an FPGA, or more likely for wearables, a completely new architecture, complete overhaul on the architecture. And that's really where the solution lies in all of this. You will see in the next few years several new architectures introduced. You'll see a lot of the low-end applications using processors like ours do low-end and lightweight neural networks. But if we want to get into that next level of neural network and enable that next level of functionality, we need to completely overhaul these architectures, and the Cortex M4 is insufficient. There's a lot of companies working on this. Ambiq is certainly one of those companies, and you'll see products that address this problem from us and a variety of others. So look for rapid improvements in this space in the very near future. So that brings me to the end. I have spent the last 15 years of my life focused exclusively on low power. It's something that I get really passionate about, and it's very much, I like to think of it like a whack-a-mole game. You knock down the first mole of power, and suddenly 5 more pop up, and so you can't just focus on the radio or just on the microcontroller or just on the heart rate sensor. You have to really focus on every element of the system. But the good news is we've seen a lot of innovation happen there, and I think that there's been a huge amount of progress in wearables as a result, and there will continue to be a huge amount of progress in wearables. And I think we can really dramatically increase the utility of these wearables in the next few years by enabling embedded coaching, by getting rid of batteries entirely, by introducing neural networks to do some really complex things. So I want to pause there and give an opportunity to answer any questions that the audience might have.
Great stuff, Scott. Thanks a lot for that. And I want to emphasize that last point about the neural networks. And we're already starting to see some of the results of neural networks in the context of wearables, and particularly as wearables become more personal health devices and ultimately medical devices. A lot of that work, for example, you've probably seen a lot of the headlines recently about wearables being able to identify atrial fib and other arrhythmia events. And that's done primarily with offline neural networks today, and analyzing post-processed data after the fact to identify whether an AFib event or an arrhythmia has occurred. And that's great work that's being done. That's huge progress. But where that's going is to be able to identify those events in real time, or even better, in predictive models, to be able to alert someone if they are on the path to an arrhythmia or an atrial fib event or some other health complication along those lines. So to the point about using neural networks, preferably in wearables themselves, and being able to run that processing in real time is certainly where the market's going, and there's a tremendous amount of opportunity there and advancement that can be driven by low power solutions that enable that level of processing going forward. So I just want to emphasize we're certainly seeing this wearables market move towards more health and medical devices, even on the consumer wearable side of things. You look at any of the recent announcements from Apple, Garmin, Fitbit, you name it, they're all moving towards personal health devices. And a lot of the things that Scott talked about are critical to making that happen. So good stuff. And wanted to, I see we do have a few questions in the queue now, but just as a reminder to everyone on the webinar, if you do have a question, please submit it through the GoToWebinar panel, and we'll start going through those now. I have to give credit to one person who submitted their question in advance of the webinar even starting, so we will start with that one and then dive into the ones that we've gotten through the webinar control panel. So Scott, the first question is, at present we have to rely on our mobile app to retain Bluetooth connectivity with wearable and interact with API over cellular connection. This is perhaps the least reliable link in our present data chain. What are the practical prospects of battery life, for example, in a wrist-worn biometric sensor, measuring our interval and submitting maybe 45 megabytes of data to an API server every 24 hours over a cellular internet? I know that was a long question, but
yeah,
what are the practical prospects there?
Yeah. So it sounds like the goal is to skip the Bluetooth link and just go straight to cellular. And today's cellular radios are really horrendous on power. Certainly high data rate. I'm not, frankly, deeply familiar with the latest and greatest on the high-end cellular side, but I can talk about some of the low power cellular standards that have emerged, and which might be a good fit here. So there is a new LTE variant that is called Cat NB1, or otherwise known as NB-IoT, and then there's a close brother of that, let's call it, that is called LTE Cat M. And both of those standards are very simple, very low cost, relatively speaking, cellular standards that can effectively use the same infrastructure as the normal LTE devices. And the penalty is that you end up with somewhat lower data rates, but you end up with dramatically lower power, and you end up with protocols that are much more comfortable and amenable to duty cycling. So, for example, you could have an NB-IoT link that spends a couple hours or 45 minutes or a couple hours asleep, and then only wakes up periodically to ping the tower and see what's going on. So you can end up with heavily duty cycled, low cost, low power radios that way. So I think that should be possible. 45 megabytes is actually a lot of data. So you'd probably skew more towards something like a Cat-M. A Cat-M link can do, I think, about a 1 megabit per second, and is probably a pretty nice option there. And so I would. Nordic Semiconductor has a NB-IoT Cat-M part coming that should be pretty decent. uBlocks has some modules that they're selling. Huawei has some modules that they're selling. So there's a lot of options out there for solutions in this space. The infrastructure is not entirely there. The software updates haven't been entirely put in place, but I think that's probably the best route there is to use something like a Cat-M or NB-IoT system.
Got it. Okay, thanks for that. Next question: how does Ambiq compare with current industry norms for power consumption?
So we're dramatically lower. We're anywhere from, if you look at active power, which is really the metric that most of our customers are judging by, we're anywhere from 3x better to 20x better than the typical products out there. And again, active power tends to be the thing of interest. At the same process node, 40 nanometers or 55 nanometers, we also tend to be lower on leakage current. It's not something we've spent a lot of time, frankly, optimizing yet. You'll see some unannounced products have dramatically lower leakage power than what you've seen from our products to date. So you'll see some nice power consumption there. But for the most part, if you're running over 100 kilohertz average, then active power is really what you need to be worried about, and we're dramatically lower than the others out there when you use a standard benchmark like Hallmark.
Got it. Another question from the same person. Does Ambiq chip support voice over BLE?
Yes, we do. So we today have a very low power voice solution that is out there today. We've worked closely with Sensory and DSP Concepts as software partners to develop a very lightweight, very low power voice stack so it can detect typical keywords. And then we've also developed the buffering infrastructure and voice over BLE infrastructure to go with that. So we have a Bluetooth product right now that this works with called Apollo 2 Blue that has an integrated BLE radio that streams the voice over Bluetooth after buffering it. So we've got a really nice solution there, and we've got a couple different customers who are going to market right now with that. So if they're interested in that, if this person is interested in that, please do follow up with us at. You can contact me at shansen@ambiqmicro.com, or you can do info@ambiqmicro.com. Both get to me, one way or the other.
Got it. Okay. Next question is, can you speak a little bit about wearables in the workplace, i.e. for health and safety? This could involve detecting, quote, bad bends or unhealthy twists and alert the wearer to unhealthy behavior.
Yeah, that's interesting. And I'll say that we don't have a ton of engagements in that space right now, although it's a very interesting one, because in our experience, we find that businesses are more likely to shell out money for things like this because there's a clear return on investment and business case for this, right? So it's the consumer wearable it's a nice to have, it's a luxury item that can end up in a drawer and it's okay. in the case of the business, we're saving money. There's real dollars and cents at stake here, so there's an opportunity to save money. So it feels to me like there's a good opportunity. I will comment that we do have some productivity enhancement products that we're supporting. One in particular, I won't say much about for confidentiality reasons, but there's a cool headset product that is a wearable device that is going to be supporting workplace productivity. And again, for confidentiality reasons, I won't say much about it. But broadly speaking, as we've seen the proliferation of virtual assistants in our homes, I think there's an opportunity for those same virtual assistants to proliferate into wearable devices. So whether it's a device that you wear on your wrist or you wear in your ears, I think that we're going to start to see more and more virtual assistants, a Siri or the Google Assistant or whatever, the Amazon. I don't want to say the name of the Amazon Assistant because I have an Echo in my office and it will chime in. But the Amazon equivalent assistant, I think that there's in the workplace there's a real use for something like that. Now I haven't spoken specifically to the health benefits there. This is more of a productivity enhancer. I want to make notes of things that are going on. But I can't say that I have any unique insight on health enhancement, though I will comment and say that the deployment of neural networks will really help there. So if I'm looking to classify a bad bend maneuver or unhealthy practice, it's something that a neural network can detect. One of my favorite uses of a neural network is the so-called anomaly detector. So this is something where you're detecting not any specific event, but you're detecting when something has changed. So imagine that you put one of these devices on your wrist, and it's something that is meant to detect. It's meant to first learn what your normal motions are. So maybe it spends a couple of weeks with you learning your normal motions. But then subsequently, it detects when your motions have changed, when you start to do something weird. So suppose you start limping funny because you're trying to avoid hurting some or inflaming some injury that you've got. It could detect that and say, hey, you know what? I don't know what's changed, but I've detected that something about your motions has changed. We might want to take a look at that. So that's one of my favorite uses of neural networks is the so-called anomaly detector. But that plus all the other neural networks that we talked about in the last few slides, I think will offer tremendous benefit if we're looking at workplace productivity and injury prevention. Beyond that, I don't know that I have any great insight.
I'm sorry, I didn't mean to talk over you there, Scott. I was just going to say there is some interesting work going on there related to identifying things like Parkinson's disease, and but prior to the onset, but also helping people with Parkinson's manage that and tracking deterioration in their movement and overall neuromotor skills. So again, the ability to do that in real time on a wearable device is really exciting. So and that can provide a little back to the question around workplace health and safety. We at Valencell are seeing quite a bit of interest in adding biometric sensors to a variety of different workplace equipment, particularly in the realm of industrial safety. So think about adding a heart rate monitor and a temperature sensor to a construction hard hat or other industrial safety equipment that workers in the field wear on a daily basis and can track their biometrics in real time and identify when they are, for example, getting close to overheating, or they're seeing a rapid increase in heart rate when their activity levels not necessarily increasing as rapidly. So there's something going on there with their body's response to whatever conditions they may happen to be in at the moment. So so there's a lot of interesting things going on related to adding additional sensors to existing health and safety and particularly industrial safety equipment. So I would expect to see some exciting stuff going on there or coming to market there in the next year or two. So last question I'm seeing here. So anyone who has additional questions that may not have submitted them yet, please do go ahead and submit those through the GoToWebinar interface. Otherwise, we'll address this last question and then wrap up. Last question here is, what sort of programming language would you recommend to achieve minimal energy usage in wearables assembly L?
Yeah, so let's start by saying most of our customers are obviously programming in C. Assembly, okay, increasingly the compilers are getting better at doing a good job. If you flip the right compiler flags, they're doing a pretty damn good job of using the right instructions. You know, for example, the Cortex M4 has a dual MAC function, or you can actually do some SIMD, some like 4-way SIMD functions, and it's the compilers get to be pretty good at taking advantage of those and thus optimizing energy. And then we find that there's a lot of compiler flags that you end up wanting to flip. So I think there's a lot of temptation to go with the lowest power solution, which generally you flip the the -0 flag to do low level, no code optimizations basically. So you get lowest power, but you don't get lowest energy. So what ends up happening there is that it takes a lot longer to execute the particular program. You're consuming less power while doing it, but the total integrated energy is actually higher. So, for example, we do tend to find the best results when you do an O3 optimization. So you do loop unrolling and all the other stuff that happens when you do the higher levels of optimization. Certainly, there are cases where you're going to want to write your own assembly code and hand optimize things, but as you know, that can be a very time-consuming thing. What we at Ambiq try to do is provide you with pre-optimized functions. So, hopefully the things that are consuming most of your clock cycles are things that are pre-optimized stacks that we're providing. So, voice recognition is a good example of that. We provide a pre-optimized stack that we worked very hard with sensory and DSP concepts to minimize the footprint of, and even today, every week we seem to be knocking a few percent off the total compute load of that thing and knocking energy down further without compromising recognition accuracy. So hopefully I'm providing you with most of what you need, and then beyond that, hopefully you can lean on the compiler, and if you can't, then you're stuck doing some level of assembly coding.
Gotcha. Well, I will say it looks like that's the last question that did come in. So thanks for all those questions. Those were great. And thanks everyone for taking time out of your busy schedule to join us here today. Hopefully you found it valuable. Just as a reminder, we will send out links to the slides and the recording of the webinar. And last but certainly not least, Scott, thanks a lot for your time and all your insights here. This has been a really insightful webinar, and we appreciate you sharing all the knowledge.
Yep, thank you. I really appreciate you guys inviting me to participate. Thanks.
All right. Thanks, everyone. Have a great day.